Welcome to InterviewPro. Let's solve another Leetcode problem today. Number of dice rolls with target sum. So we will be given n dice and each die will have k faces numbered from 1 to k. Let's look at the first example given in the problem. We have one die and the die has 6 faces and the target is 3. So how many possible ways are there from this one die to get the target 3? Obviously only this 3, right? So each face has a value starting from 1 and ending at 6. So there is only one die which can give us the target 3. So the output is 3. Now let's look at another example where we have two dice. Each die will have 6 faces and the target expected is 7. So how many combinations of these two dice can give us the target sum 7? If the first die value is 1, to get the target 7, what should be the second die value? 6. Or if the first die value is selected as 2, then the second die value will be 5 to get the sum 7. Similarly, we have 4 other combinations as well. So the output is 6. Let's try to understand how to solve this problem. So we have two dice, right? So let us assign an index to each of these dice. Let's start with 0. So if we have two dice, the indices would be 0 and 1. We need to find out what is the sum for each of these configurations. So initially, when there are no dice at all, the initial sum would be 0. So we have to decide what is the value for the first die. So for the first die, we have 6 faces because k is given as 6. So we can select any of these faces, right? So if we select 1, what should be the value for the second one? So the index of the second die is 1. And what is the sum we have achieved so far? It is 1 because the initial sum was 0. When we selected the face value of the first die as 1, the sum is 1. Similarly, if we select 2 for the first die, when we reach the dice of index 1, the current sum calculated so far is 2. Then if it is 3, then it would be 1 comma 3 and so on up to 1 comma 6. Now the combinations for the first dice is completed. Let's say we selected the value 1 for the first dice. Let's see how many combinations are there for the second die. So the sums calculated so far is 1. If I select the face value 1 for the second dice, it would be 2 comma 2. I mean, by the time we go to the next iteration, which is the index 2, the calculated sum would be 1 plus the face value 1, which is 2. Similarly, if I select the face 2, then it would be 2 comma 3. 2 is nothing but the index of the dice. So when we select value 6 for the second dice, the sum would be 1 plus 6, which is 7. All possibilities for the second dice is also completed. Now we'll move to the end of the iteration. So when the index is 2, we don't have any more dice to compute. And also when we have calculated all the combinations for these two dice, we'll check if any of this combination has given the sum which is equal to target. Is this equal to target when the combination was the first die was 1 and the second die was 6, the sum was 7. So 1 comma 6 is one of the combinations. Let's take another combination. For example, if I take value 6 for the first dice, what would be the sum so far? Initial sum is 0. The sum after taking 6 for the first die is 6. So for the next index, which is 1, we'll calculate what are the possible combinations. So this also has 6 faces. So if I take 1, the previous sum was 6. If I take 1 for the index dice of index 1, then it would be 6 plus 1, 7 by the time I go to the next iteration. And if I take 2, the sum would be 6 plus 2, which is 8, which is greater than target. And for all these other combinations also, we'll get the sum greater than target, which obviously wouldn't lead us to the possible combination, right? So it's waste of calculating these combinations. So the other combination that we got is 6 comma 1. So we can calculate all the combinations for all these values as well. And look at this, 2 comma 7 combination is already calculated in this path. And we got the same combination for this path where we selected 6 for the first die and 1 for the second die. So using memoization, we can simply return the values without computing them again. So when we move from one iteration to another iteration, what are the two things that we need to consider? The index of the dice and the sum calculated so far. So when we go to the next iteration, we just increment the index and add the face value that we selected to the previous sum. The face value is represented as I. So let's see how we can code this. I'll be coding this in C Sharp. So let me declare the required variables first. We want a memo because we know that the combinations are going to be repeated in the tree. So we want to declare a memo. And this is a 2D array. Let's say memo. And let's initialize this in the main function. Int new int of n plus 1 and target plus 1. We are taking n plus 1 and target plus 1 because we saw that once we calculated the value for index 1, we went to the next iteration where the index was 2. So we are taking extra space here to deal with the index out of bound situations. Then in the solution, it was given that the answer may be too large, and if the answer is too large, we can return modulo of 10 power 9 plus 7. So let's declare a variable called mod, which is 1, 2, 3, 4, 5, 6, 7, 8, followed by a 7. Let me declare two more variables here so that we don't need to pass these n and k and target to all the iterations. I'll make it global. So what is n? It is the number of dice. So n dice. Then we have a number of faces for each of these dice. Then the expected sum, which is nothing but target. Let me initialize these values here. So dice equal to n, faces is k, expected sum is target. Also, let's initialize the values of memo with -1 initially. So for I0, I less than or equal to n, we took n plus 1, right? So we should iterate till n. I plus plus. Same for j equal to 0, j less than or equal to target, j plus plus, memo of I comma j equal to -1. I'll create a method called dp, which would return the number of combinations, and the input would be index of the dice. So dice index and previous sum, the sum which was calculated so far. So the final value returned would be dp of 0 comma 0. We'll start with the dp of 0 to 0 and iterate until we reach the last die. So if we have considered all the dice, then the dice index would be equal to dice. In such case, we need to check if the target sum is achieved or not. So if the previous sum is equal to target, then it means that we got one combination. So return previous sum equals expected sum, then return 1, otherwise return 0. If we did not consider all the dice yet, or if we are still at the first dice or the second dice and there are few more dice to be computed, then we need to check if the value or if this combination is already calculated or not. If it is calculated, it would be present in this memo. So if memo of dice index and previous sum not equal to -1, because the initial value is -1. If this was already calculated, then the value would be overridden by some other value. So we'll simply return memo of dice index and previous sum. If it's not present in the memo, if the value is not already calculated, then we need to consider how many possible combinations are present. So let me declare a value here. So int count equal to 0. Now we need to consider all the faces for each die, right? So let's loop from int, I'll say face equal to 1. The faces are numbered from 1 to k. So I'll loop from 1 to k, which is nothing but faces. Face less than or equal to faces. Face plus plus. If you remember, I mentioned that you don't need to calculate for all the faces. If the sum is exceeding the target value, then there is no point in calculating the combinations, right? So what we can do here is math.min of faces or previous sum expected sum minus previous sum. So if the previous sum plus face is greater than expected sum, we don't calculate it. So that can be obtained by using expected sum minus previous sum. So how do we calculate the number of ways? We'll simply call the dp function again with the dice index incremented by 1 and the previous sum plus the face that we have selected. Finally, we'll assign this value to the memo. Dice index comma previous sum equal to count, and then return memo of dice index comma previous sum. Let's try to run this program. So one of our test cases is failing. This is because the value is large here. Whenever there is a large output, we need to apply this modulo. So where do we get that large sum? In each iteration. Let's apply this modulo here, percentile mod, and run the solution. All the cases are accepted, and let me submit this. The solution is accepted. Now let's try to do the same thing using bottom-up approach. What we did so far was top-down approach. We started with 0, 0, then tried to calculate the different combinations. Once we reached the sum 7, we backtracked and calculated the number of combinations that gives us the expected sum. To solve this using bottom-up approach, I have taken a matrix with the extra space to handle the out-of-bound cases. So this represents the dice index and this row represents the sum that we have calculated so far. In the top-down approach, we saw that when the index is 2 and the sum is 7, we considered that this is one possibility because when the index is 2, it indicates that the first these two dice are already computed and the sum which is equal to target is already achieved. So there is one possible combination here. So this is going to be our base case. When the index is 2 and the target is 7, we are going to assign the value 1 by default because it indicates that we got one combination here. For all other target sum, it would be 0 because if the index is already 2 and the sum is not yet 7, that means there is no combination yet, right? So let's calculate for the dice at index 1. For dice 1, if the previous sum is 0, what are the different possibilities that I can check? I can put 1, I can put 2, 3, 4 and 5. 4, 5 and 6. So now since the target sum is 7 and the sum that we have so far is 0, we can check till we get the sum 7. So I have all these combinations here. So if I select the phase 1, what would be the sum? It is 1. For the sum 1, what is the combinations that are available so far? 0. And for the combination, if I take phase 2, what are the combinations that are available for the sum 2? 0. Similarly, for all the 6 possible sums, we get 0 combinations. So 0 plus 0 plus 0 plus 0 is 0. Let's say we have the sum 1 so far. What can be the value selected for dice 2? If the sum is already 1, how much sum we need to add to get the target? It is 6, right? So we can choose the faces that can give us the sum 6. If I add face value 1 to the already existing sum, what would be my sum? 2. And what are the possible combinations for the sum 2 that we got so far? 0. For if I add the phase 2 to the previous sum, what would be the current sum? 3. And what are the possible combinations available? 0. Same for 4, 5 and 6. Now, if I add the phase value 6 to the previous sum 1, it would be 7. So what are the possible combinations that I have? 1. So if we add all these possibilities, the output would be 1. Let's say the previous sum is 2. Then what is the face value that I can select so that my target is 7? I can select from values 1 to 5 because if I add 6 to 2, that is going to give me the sum 8, which is greater than the target. If I choose the phase 1 and add it to the previous sum, what would be the current sum? 3. 3 is not our target, so the number of possibilities is 0, which we have already calculated. Now if I choose the phase 2, adding it to the previous sum would give me the sum 4, which has 0 possibilities. Then adding 3 would give me the sum 5, which has 0 possibilities. Adding 4 would give me 6, which has 0 possibilities. Adding 5 to 2 would give me 7. And what are the number of possibilities? 1. So if you add all these counts, it would be 1. Now, if the previous sum is 3, then what is the sum that I can add here? With any face value that would give me the sum 4 because 7 is the target. We already have sum 3. What is remaining? 4. And how many faces can give me the value 4? Only this value, but I can still compute this 4. If I compute the value for 5, adding 5 to 3 would give me 8, which is greater than the target. So we can ignore these two values. So if I add 1 to the previous sum 3, what is the sum? 4. And the possibilities are 0. If I add 2 to 3, the sum is 5, possibilities are 0. 3 to 3, 6, 0 again. And if I add 4 to 3, it would give me the sum 7. So the number of possibilities to get the sum 7 is 1. Adding all these possibilities would give us the output 1. For the previous sum 4, these are the different possibilities and the output is 1. For the previous sum 5, we have only 2 possibilities and the output is 1. For the previous sum 6, we have only one possibilities, that is to add the phase 1. By adding the phase 1, what would be our total sum? 7. For the 7, how many combinations are there? It is only 1. So here we'll place the value 1. Now if we move to the first dice, the previous sum is 0. So I still need to find the sum 7. So how many possible combinations that are allowed in the first dice? It can be 1 to 6. So if I add 1 to the previous sum 0, what would be my answer? 1. So for the sum 1, how many combinations are there which we have already calculated? It is 1. And if I add 2 to this previous sum 0, what would be the sum? 2. And what are the combinations that we got so far? 1. Similarly for 3, 4, 5 and 6, because adding 0 to the last phase, which is 6, would give us the target sum 6 and the number of combinations are 1. So adding all these possibilities would give us the value 6. We don't need to calculate all the values for this, but if we calculate, we would get these values. So the output would be 0, 0, which is 6. There is a typo here. The output is actually 6 when we have two dice with each value 6. Now let's try to code this using bottom-up approach. Let me declare another variable here, another method here. Let me name it as bottom-up only, and I'll pass n and k in target. We don't need all this, but let me comment this, and instead of BP it would be bottom up, and I'll send all the values and k and target. So first we need an array, and I'll call this array as dp only. Dp equal to new int n plus 1 and target plus 1. So what was our base condition? dp of n comma target equal to 1. What does this mean? We have already selected faces for the n dice, and the target is equal to the required expected target. In that case, it means that we already have one possible combination. Now we need to calculate for the actual dice index. So for int, let's say dice index equal to n minus 1, as we are moving from the bottom to top, dice index greater than or equal to 0, dice index minus minus. Then we check for the each of this current sum. So for int current sum, or we can say previous sum, actually previous sum equal to 0, previous sum less than or equal to target, previous sum plus plus. Now we need to calculate all the possibilities for all the faces of each die. So for int face equal to 1, because the faces are starting from 1 to k, face less than or equal to k, face plus plus. And we also discussed that we don't need to calculate for all the faces, because if the sum adding face to this previous sum exceeds target, then it's of no use. So we'll say math.min of k comma target minus the sum calculated so far. Whatever is the minimum, we'll calculate only till then. So count equal to count plus dp of the next dice index and the sum calculated by adding the face to the previous sum. So dice index plus 1 comma previous sum plus face. And if the sum is too large, so percentile mod, we have to apply the modulus. So percentile mod dp of dice index and previous sum equal to count. And what do we return at the end? dp of 0, 0. Let's run this. Previous sum does not exist. Okay, this has to be inside this for loop. We have calculated the combinations for all these phases, and we need to update the DP array for these two combinations. Okay, I forgot to add the return statement here. All the cases are accepted. Let me submit the solution. The solution is accepted. Coming to time complexity of both these approaches, we are calculating for all these combinations. So for n dice, we are checking for each of the target sum, and in each of this iteration, we are checking for all the faces of each of the dice. So time complexity would be n into k into target. Coming to space complexity, we are using DP array, which is of size n plus 1 target plus 1, which would be n into target in case of bottom up. In case of top down also, we are using the memo here. So this memo size is equal to n plus 1 target plus 1. So the complexity is n into target. But in DP, we have an additional space which is occupied by the recursive call stack. For each of this dice index, we are making a recursive call. So it would be n extra calls. So n into t plus n, which would ultimately give us big O of n into t. The extra additional n function calls are saved using this bottom-up approach. I hope the solution is clear. If you like the content, please like, share, and subscribe to InterviewPro. Thank you.